Hey there, folks, back here with one more video for the day where I want to walk through with you one of the, one of the more important definitions that we have in our study of calculus. It's going to actually be a definition that we're going to come back to in Calculus 2 and rely upon pretty heavily initially when we start looking at application of this idea. And that is the definition of the definite integral. All right, let me bring this over into view here. I do want to get into a discussion of the definition of the definite integral. I do want to go through this note set with you here where we do spend some time on this definition. And what we're going to see is that this idea fundamentally is connected to the idea of finding the area trapped by a function, right? The area trapped between a function and the x-axis over a given interval of our independent variable. Right? And that's how we're going to begin developing this definition. All right? So we do go back to a familiar example here. Excuse me. Where we consider finding again that exact area trapped between the curve f of x equals x squared, right, and the x-axis over values of x in the interval from 0 to 10. And as we had noted in the previous section, we could approximate this area using some Riemann summations. And we could make this approximation more precise by increasing the number of subintervals we used in our approximation. All right, as we increased our number of value, as we increased the value for n, right? N being, again, this number of subintervals. We had looked at the case for using 5 subintervals. We had looked at the case, I believe, for using 10 subintervals. And I struggled a little bit with just some notation getting the case for, what was it? The case for 500 intervals, right? In the approximation. All right, doing that on our calculator. All right. Well, we are going to look again at that case and now consider finding the exact area, right? What we had done before in the previous section was look strictly at an approximation, a really good approximation when we increased our number of subintervals, all right? Where in this case, what we're going to consider doing now is using an arbitrary number of subintervals. All right, we're going to consider the exact same setup we had for our Riemann summations in the previous set of notes and consider it now for an arbitrary number of subintervals, just for any value of n being an integer value representing the number of subintervals we subdivide 0 to 10 into. So if n is some arbitrary value, that means our delta x would be given by 10 divided by n, and our value x sub k, which for a right Riemann sum would be a plus k times delta x, would be 10k divided by n. And if we substitute that into our function where this quantity is going to be squared, right, 10k divided by n quantity squared, let's substitute that in here. Right, into our function for f of x is going to yield the quantity 100 over n squared times the quantity k squared. And I do group them this way specifically because if you remember, when we apply the summation to this, the summation is in terms of the index of k. Right? And if we do set up that Riemann sum in general for this arbitrary number of subintervals, we do end up with that Riemann summation given by this quantity seen here, where we are going to take our value f at x sub k, seen above, this quantity, and multiply it by our value of delta x, which again we found to be 10 divided by n, where when we think about simplifying the argument of this summation, the 10 times, or the 10 over n times the 100 over n squared actually simplifies into the statement 1000 over n cubed, which is a constant multiple in the context of our index k. So we can factor that out of our summation, and we're left with really just summing arbitrarily from k equals 1 to n the quantity k squared. And if we sum from k equals 1 to n the quantity k squared, we are left with the quantity n times n plus 1 times 2n plus 1 all divided by 6. If we recall our shortcut, the little helpful formulation for summing our k squared values from 1 through n did have the formulation n times n plus 1 times 2n plus 1 all divided by 6. Where with a little simplifying, right, the 6 and 1000 both have a factor of 2, and that'll simplify to 500 thirds. And that quantity n times n plus 1 times 2n plus 1 over n cubed has a common factor of just n. This common factor of n right here can cancel with one of these n's, leaving behind an n squared in the denominator. And if I arrange those over each other, right, we can build this statement seen here. Simplifying the 1006 to 500 thirds and canceling this common factor of n, leaving behind an n squared in the denominator. Right? If we think about it in general now, this is a Riemann summation calculation for using any n subintervals. Right? In general, that Riemann sum is given by this formulation seen here. Right? And where I was struggling before with 1000 subintervals, we could simply substitute that into this equation and calculate it for using 1000 subintervals. Right? It would be 500 thirds of 1000 plus 1, which would be 1001, times 2000 plus 1, which would be 2001, all divided by 1000 squared. All right. And we can see if we do substitute in different values for n, if we go back and we substitute in a value of n equal to 5 into this formulation, it does give us 440 units, as we had found in the previous section of notes for 5 subintervals. If we substitute in the number 100, we do get the calculation we saw in the previous set of notes, given by 338.35 in value. And as we had just noted, if we perform the calculation for n equal to 1000 subintervals, it's going to be 500 thirds times 1001 times 2001, all divided by 1000 squared, which is equivalent to 1 million in value. If we do a little simplifying of that statement, it does simplify uniquely into this calculation, 667,667, all divided by 2000. Notice it kind of matches up with this calculation up here. Kind of uniquely, there's a bit of a pattern forming there in this case, and there is. Right? And we do see that simplifies to, what, 333.8335 in value. Right? As I had noted, the value is actually 1000 thirds. So it's 333.333 repeating. And we're pretty darn close to that. We're about half a value away from that, 1/2 a unit squared. All right. Now, to get exactly that value that I promised is 1,000 thirds, we could actually apply the use of a limit. We can go back to this Riemann summation value that I have, given in general terms of n, by this value I'm highlighting here, that 500 thirds times n plus 1 times 2n plus 1 all divided by n squared. And I could ask myself, how does that quantity behave as n heads to infinity? Right? I could push this value of n, seen in the summation, towards the value infinity by using a limit, applying a limit to that argument. Ooh, excuse me, folks. Oh. Ooh, pardon me. Usually my sneezes come in threes. We'll see here. There's going to be one more tonight, I can tell. All right. So if we continue to evaluate this limit, we will notice that 500 thirds is a constant multiple, and it'll factor itself outside of the limit and become just a constant multiple of the limit. Now, if we consider evaluating the limit as n heads to infinity for this rational form here, we will note that the limit of this rational form will behave like the ratio formed by the leading factors. Sorry, the ratio formed by the leading terms. If we expand n plus 1 times 2n plus 1, the leading term would be 2n squared in the numerator. Putting that over an n squared in the denominator, my limit as n heads to infinity for that quantity would be 2n squared over n squared, which simplifies. It simplifies to the constant of 2. Right? The L'Hopital's would give you the exact same result. And if we think about it, we have 500 thirds times the limit as n heads to infinity for 2, and what's the limit of a constant? It's just the value of 2. So 500 thirds times 2 yields the value 1,000 thirds. As I had said, the value of this exact area is 1,000 thirds of a units squared, or 330.33 repeating. All right? And the way that I found that was developing the formulation for the Riemann sum for an arbitrary value of n, and then applying a limit as n heads to infinity to that Riemann sum calculation. All right? When I take a limit and I apply it to a Riemann summation, whether it's a right, left, or midpoint, or any arbitrary x value, x sub k value, what will happen is it will always approach the exact area, right, of that trapped region for any function over any interval of a from a to b. Right? And when we apply a limit as n heads to infinity to a Riemann summation, what we actually form specifically is what's known as the definite integral calculation. What we had just performed here is what's known as a definite integral calculation. Right? I think the first thing I do is I draw the conclusion, thus the exact area, all right, trapped under this curve, f of x equals x squared over values of x in this interval from 0 to 10 is given by 1,000 thirds of a unit squared, right? Or 333.33 units squared, right? And then I go on to note, when we do apply a limit to a Riemann sum, the result is going to be known as what we call a definite integral. And the calculation produces what we're going to call a net area trapped by our function. All right? A net area trapped by our function over that closed interval from A to B. Right? I should probably say here over the closed interval from A to B. For values of our independent variable x. All right? And this is what we see given in the definition of a definite integral, along with some additional notation. All right? In the definition of the definite integral, right, we assume y equal to f of x is integrable over this interval x over values of x in the interval from a to b, meaning that we can go about finding its definite integral. Right? Well, its definite integral of f then is going to exist over this interval. The definite integral will exist over this interval, and it's going to be given by the limit as n heads to infinity for that Riemann summation, which is also equal to the following notation, where what we see with the highlighted notation here resembles the calculation for an antiderivative. The antiderivative that we also had noted in the previous section of notes can be known as the indefinite integral calculation. This here is specifically known as the definite integral calculation. And the reason it's the definite integral calculation is because it's definitively happening over a set of boundaries that happen from A to B. Whereas, in the case for the indefinite integral calculation, we did not have boundaries on the calculation. The boundaries happened over, well, I should say the calculation occurred over an unbounded region of x. And when that occurs, what we obtain is what we go back and note or understand is going to be our indefinite integral or our antiderivative value. But if I take an integral value and I perform it over a bounded region, we're going to find a region bounded from A to B for our values of x, we are going to be calculating what we call a definite integral, and what it is going to represent is the limit of a Riemann summation in its calculation. And what we're performing again is the process known as integration, right? We're performing integration to calculate a definite integral, to perform a definite integral calculation, just like integration is used to talk about performing an indefinite integral calculation or calculating an antiderivative, where the limit of the integrations are described by the boundaries on that closed interval from A to B, right? What A and B become known as are the limits of our integration. Definitive integrals have limits on that integration. A and B become the boundaries on those limits. Well, become the limits of integration on that boundary of integration. Whereas indefinite integrals do not have limits of integration. All right? And f of x, the argument of an integral, right, this value that we're applying the integral operator to, is actually specifically known as the integrand. Right? Becomes what we call the integrand. It's called the integrand. Right? The function that we're applying a definite integral calculation to is what's going to be known as the integrand. Right? In our previous case, hold on a second. I'm going to just police where I'm heading with this and take a quick pause. Let me see. I do think I maybe want to state one other thing here that I maybe missed in my notes. Let me see. I'll be right back here. Let me transition this over and pause this now. All right, I'm glad I looked ahead. There were a few things I wanted to include there that I had skipped over when typing this up, folks. So I'm glad I took a peek here. So let's relate this back to what we just calculated, right? That was one thing I had forgotten to do here, and I wanted to make sure I do. So in the previous calculation, right, of this limit applied to the Riemann summation for the function f of x equal x squared over x in the interval from 0 to 10, the definite integral is actually given by this statement seen here, right? It's this definite integral calculation that happens over a limits of the integration given by a lower boundary of 0 and an upper boundary of 10, right? That's applied on the integrand, the being x squared with respect to variable x. And it is equivalent to the limit of the Riemann summation in this case that we set up previous, which we have shown is equal to 1,000 thirds units squared in value. And it all illustrates the following, what we're going to say is area of space for the moment, right? This exact area of space trapped in this illustration is 1,000 divided by 3 units squared, or about 333.3 repeating units squared, right? That's all equivalent to that limit of the Riemann summation that we set up and calculated earlier, which is nothing more than the definite integral calculation from 0 to 10 for x squared dx, right? What we might think of at the moment is this is a shorthand way of asking for this area for the case of f of x equals x squared over x in this interval from 0 to 10. When we see this notation seen here for the definite integral, the way we want to understand that and interpret that is as a area calculation. And I should be a little more specific here. In fact, it's what's known as actually a net area calculation. We throw the word net in front of that, right? And if we think about net, you can have a net profit, which is like, what is it? It's all your revenue minus your expenses, your costs, will give you a net profit, right? A net gain. That's right. It's including all your gains and your losses, right? Here we talk about a net area, right? In the previous case, we just called it area, right? Because x squared, f of x equal to x squared, was actually greater than 0 for all values of x, and particularly for all values of x in the interval from 0 to 10. However, if we're speaking more generally, right, f of x, the dependent value of our function, right, the function that determines the shape of this graph, can be both positive or negative over values of x in the interval from a to b. We could consider definite integral calculations where that curve dips above and below the x-axis several times over our interval of the definite integral calculation. And when it goes below the x-axis, the function's dependent values become negative. And if we put those values into the summation part of the Riemann sum for function f at x sub k, they're going to yield negative products when multiplied with the delta x, which is always going to be a positive length. So over regions that form below the x-axis, you're going to be calculating areas that have negative values. Negative values due to the fact that the output of the function at those x sub k values are all going to be negative. They're not negative in terms of size, however, they're negative in terms of direction. And when we total up all these negative directed, all these areas that form in the negative direction with all these areas that form in the positive, we are going to have some canceling happening between positive and negative regions of area. So our net area is going to behave not quite as we might anticipate an area to behave. We could even end up at times with zero net areas or negative net areas when we actually are looking at physical regions of space that have size to them, right? It's just that the size is forming above or below the x-axis. Above and below the x-axis, I should say, in those cases. To begin with, right, the definite integral of y equals f of x over the interval from x over x in the interval from a to b yields a value representing what we call the net area trapped between the curve of f and the x-axis over values of x from x equal to a to x equal to b. Net area describes both size and direction of a trapped region of space in R2. Total net area describes the total positive area trapped above the x-axis, summed with the total negative area trapped below. All right. I again reiterate that. Where we are looking at area that forms in two directions, either above or below the x-axis, where you will get for areas above positive values and for areas below negative values, and when totaled, they will start to cancel with each other at times, right? Leaving the difference of the physical areas forming in these two different directions, right? And if a negative area is bigger than a positive area, we would actually end up with a negative total net area. Let me see if I think I have an example that follows. Yeah. Consider the following illustration of net area trapped by the line f of x equals 1/2 x minus 3 over values of x in the interval from 0 to 10 again. If we look at just values of x from 0 to 10, and the line 1/2 x minus 3 seen here, there is a trapped region of space between the line and the x-axis that forms over values of x from 0 to 10. And what we can see is some of this region forms below the x-axis, and I've gone ahead and shaded it here in red, and some of this region forms above the x-axis, which I've left here shaded in blue. When we calculate the red net area, what we're going to find is that's going to actually give us a negative value. Negative because all of the values for the heights of our subintervals are all going to give us negative dependent values along this vertical axis. Whereas these are all going to yield positive values for net area because all those subintervals will all yield positive values along this vertical axis for the height of those bars that form. All right. And as we can see in the illustration, it does look like the region in red is going to be larger than the region in blue. So there's a good chance that we're going to end up with a negative net area in total. And if we look at the regions here, actually we can consider calculating these with a little bit of geometry. In the case of a line, right, the region trapped by the curve here is triangular. Right? The two regions that we form here are triangular regions where we can rely on just a little bit of geometry. If we consider the net area trapped below here, it is a triangle with a base measurement of 6 and a height of -3. Technically positive 3, but because it forms in the negative direction, let's say -3. And when we take -3 times positive 6, that will yield -18 in value. Cut that in half, because we have a triangle, not a rectangle, and that will yield -9 units squared. Now, I hope I did my math right here. Again, here we do have two triangles form, and I did, thank goodness. I was like, oh, did I cut them all in half? I think I did. Let's double check, right, as we go through this. So yeah, in this first calculation from 0 to 6, the definite integral calculation would be set up as this. It would be an integral that happens over the bounds from 0 to 6. The limits on the integration would be from 0 to 6. Our integrand would be the function 1/2 x minus 3. We'd be applying the definite integral calculation to this function. The boundaries being this interval over which we're looking at the definite integral calculation. And since variable x is of interest to us in the calculation, and we perform that calculation here with 1/2 x minus 3, when we look at the picture for the description, we calculated that using the area of a triangle and found that to be -9 in value. Right? And as we had said, the -9, meaning that we have 9 units squared of area that actually form in the negative direction for our function of f. Now, if we calculate the area of the blue triangle, it has a base of 4 and a height of 2. Positive 2. Positive because over here on this side, from 6 to 10, function f is above the x-axis. So if we have a base of 4 and a height of 2, that gives us 8 when multiplied together. Cut that in half, and we should have that triangle measure 4 units squared in the positive direction. Let's double check that number. And yes, we can see here that value is going to be given by the definite integral that happens from 6 to 10, applied to the integrand of 1/2 x minus 3, and as we have noted here, it does equal positive 4 in value. And I'm just highlighting the positive 4 because it is positive, meaning that the 4 units squared of area are forming in the positive direction. All right? So in this picture, we have 9 units of area form in the negative direction, 4 units of area form in the positive direction. So if we think about what they total to overall, over values of x from 0 to 10, well, the total of -9 and 4 is -5 units. The net area over that region would be -5 units of net area. And that is what we see happen in our calculation. All right. The definite integral over the entire region from 0 to 10 for 1/2 x minus 3 would actually be equal to -5. Right? It would be equal to the 9 units that form above. Oh, careful. They'd be equal to the 9 units that form below plus the 4 units that form above. Now, I'm not going to double the 4 there. I'll just leave it in the parentheses as positive 4, representing those two individual areas. Now, what we can see when added together, that does equal -5 in value. Right? In a sense, we can think of this integrand from 0 to 10 as being the integral that happens from 6 to 10 being added to the integral that happens from 0 to 6. And if I set it up that way, specific, yes, that would correspond to that first integrand being -9, or negative That first integral being -9, and the second integral being +4 in value. When we think about integrating from 0 to 10, we can consider it as being this calculation seen here. Let's go ahead and move this down. Put that right below here. All right. That is the meaning of net area. And when we perform these definite integral calculations, we are calculating this geometrical concept of area that can form in two different directions relative to the x-axis. Where above the x-axis, it gives us a positive area, and below the x-axis, we end up with a negative area. All right. Physically, we have, 9 units of area and 4 units of area. We have 13 units of area in total, physical area. But in terms of net area, total net area is -5 units. When totaled together, the negative and the positive regions cancel with each other, leaving 5 units below the x-axis. All right. That's the concept of net area. Now, there are a few properties we're going to go through here that are helpful when calculating and interpreting definite integrals. Let me go through these with you. I'll give you a few examples that will follow here. First of all, in these properties, we're going to have a couple of functions, f and g, are just going to be integrable, and they're over intervals that contain a, b, and p. All right? Well, first things first, if we perform a definite integral calculation from a to b for f of x dx, we can actually reverse the order of those bounds on our limits of integration if we take the opposite of our calculation. Order of the boundaries on our integration can always be reversed if the calculation becomes its opposite. All right? That's going to become a useful property to us. If we integrate over boundaries that don't change, that stay the same, that are really at just a single bound, well, that will always equal 0 in value. That essentially just means we're integrating over a line. We're trying to find the area of a line trapped under the curve, and lines don't have areas. We actually need to have an interval form for that area to form. Otherwise, at just a line, the trapped space is equal to 0 units. Right? Just like antiderivative operators, the definite integral will distribute itself across a sum or difference. That's what this third property is saying. And the fourth property is also similar to what we saw for indefinite integrals, antiderivatives. And constant multiples will factor themselves out of definite integral calculations. This constant multiple c factors itself out. I should also add up here. Also, c is any constant. Let's make sure we add that in there. All right. Now, we can also split up an integral from a to b into a sum of two separate integrals with different boundaries. Right? From a to p and from p to b, right? For our function f of x dx, right? If our function is integrable over an interval that contains all three values a, p, and b, right? What we're saying specifically is something similar to what we used directly above here. This integral here is equivalent to this statement seen here. The left-hand side is equal to the right-hand side. The integral from 0 to 10 was separated into two separate integrals, one that happened from 0 to 6 and the other from 6 to 10. because this function was integrable over the entire interval from 0 to 10 that included all three values 0, 6, and 10. All right? Take note. That's what that fifth property is saying. And then if we look at taking the definite integral for an absolute value of the function, one thing we will note is the absolute value is always going to be forced to be positive. So the function itself will always be trapped above the x-axis. So what you're going to have to do actually is sum the net areas that form above the x-axis and take away from that the sum of the areas that form below. For example, if instead of up here wanting the definite integral from 0 to 10 for f of x equal to 1/2 x minus 3, and I wanted it for the absolute value of that quantity, this portion that forms below would actually rotate around the x-axis and now form above. And the net area that we would actually calculate would be this positive area 4 minus this negative 9 for this net area, which would be plus 9. And we would have 4 plus 9, or 13 units squared, for the definite integral of the absolute value of that function. All right? That's what this property for absolute value is saying. Calc 2, we're going to see some calculations involving absolute values. That's why this is kind of appearing here. Right, kind of preparing us for that. And then a few others. If f of x is always greater than or equal to 0, your net area will always be bigger than 0. We saw that for the x squared function. All right. If f of x is bigger than g of x, and they're both bigger than 0, right, for all x in the interval from a to b, then the net area trapped in f of x will actually be bigger than or equal to the net area trapped in g. Because if f of x is always above g of x, what's trapped below it will always be bigger than or equal to what's trapped below g if they're both bigger than 0. And then lastly, if function f is always trapped between two values, two constants m and m, little m and big M, right? Then the definite integral will always be trapped between m times b minus a and big M times b minus a, where this kind of goes back to what we saw in the previous case where we were looking at forming rectangles around our regions of interest. Cap M times b minus a that I have highlighted here is a rectangle that the entire definite integral will form or fit into. Little m times b minus a is a smaller rectangle that this net area will always be bigger than. Right? So our definite integral, our net area, will always be trapped between these two total net, between the area in these two rectangles, right? Which I probably should say are both being greater than or equal to the value of 0. And that kind of shifts us down here, so I'm going to just move this over like I did the other line. Right? A couple of useful properties. Let me go through a couple of quick examples here. These are kind of unique because we can apply these properties without having a specific function. For example, I could say, let's determine the definite integral from 7 to 10. Hold on a sec here, folks. I'm going to take a quick momentary break. I am back. Let's see here. One quick thing I want to do is I want to go back here. Not only do I want to say also c, little m, and little m are constants. Oh, and cap m. All right. are any constant values. Let's say it that way. Here, then, all of these being greater than or equal to, yeah, we can be safe with saying that, 0. All right. Now, example, right? Again, these are kind of unique because we can apply these properties without having a specific function. Here I say determine the definite integral from 7 to 10 for function f of x dx. And I don't tell you what f of x is. But I do tell you from 0 to 10, the definite integral is equivalent to 23. And from 0 to 7, the definite integral is equal to negative 11. Well, applying the property above for the summation here, right, this fifth property, I can go through and show, first of all, from property 5 that the integral from 0 to 10 must be equal to the integral from 0 to 7 plus the integral from 7 to 10. Implying that if I solve for the integral from 7 to 10, if I subtract the one from 0 to 7 from both sides, right, I'll be left with the integral from 7 to 10 on one side, and it'll equal the integral from 0 to 10 minus the integral from 0 to 7. Where here I'd be looking at taking 23 minus negative 11. And what I would end up finding is that the integral from 7 to 10 must be equal to 34 in value. 34, because that's the only way that I could take negative 11, add it to 34 to make it equal 23 in value. All right? And this is using that property 5 from the list above. All right? So you can do these little algebraic manipulations with these formulas. All right, and I draw that conclusion there. And then I just show some illustrations of these ideas. All right. Here we're going to assume that f of x is going to be bigger than 0 for x less than 3, and f of x is going to be greater than or equal to 0 for x greater than or equal to 3. And we're also going to assume that the integral from 0 to 3 for f of x is equal to 10, and the integral from 3 to 6 for f of x is equal to negative 18. Along with the integral from 0 to 3 for g of x being equal to the value of 4. So we have a few assumptions in place here. All right. Let's keep these all in mind as we do this calculation. All right. And this should make sense with what we said above. F of x is bigger than 0 for x less than 3. So from 0 to 3, I should have a positive result there, and I do. Which means from 3 to 6, where x is greater than or equal to 3, f of x is actually smaller than or equal to 0. Which means I should have a negative result there, and I do. Now for g of x equal to 4, we really don't have much information about g of x behavior to be able to check that this result of 4 makes sense. Now, again, from property 5, we could go back and note, if I want the definite integral from 0 to 6, then I could just add together these two results, the integral from 0 to 3 with the one from 3 to 6. I could add 10 to negative 18 and get negative 8 in value. So the total net area from 0 to 6 must be equal to negative 8 units squared. All right? That's all from property 5. If we look at property 1, right? Property 1 just says if I want to find the antiderivative, or I should say definite integral, from 6 to 3 for my function, well, that would be equivalent to the opposite of the definite integral from 3 to 6. And from 3 to 6, it's negative 18, so it'd be the opposite of negative 18. It'd be equal to 18 in value. That's what property 1 is telling me. Right? That's how it could be useful. It can reverse your bounds when needed. And you can, at times, that might be necessary. Property 2 just says, well, if I find the antiderivative of any of these functions from 6 over, well, I should say over no interval size, just over the same value for the upper and lower bounds, that will always equal 0. And that's what property 2 tells us. All right. Property 4, well, that was the absolute value one. And what it says, if you're interested in the absolute value of function f of x is a definite integral from 0 to 6, well, you're going to want to take the region that forms above from 0 to 3 that has an area of 10 and subtract from it. Remember, the rule says it's going to be minus. It's the sum of the net areas for y equal to f of x greater than 0. All right? For the area that forms above, minus the sum of the net areas for the regions that form below the x-axis. All right? Well, here in this example, that regions that form above is from 0 to 3, as we had noted earlier. So that's the 10, minus the region that forms below for 0 to 6 would be the region that forms from 3 to 6. So we're going to take away negative 18, which gives us the absolute values result of 28. Right? We have to convert the minus net area into a positive result, and we do that by subtracting it or taking its opposite and adding that to the net area that forms above to actually find the absolute value of our function. And what this actually also yields is the physical area trapped in that entire region. Another way to think about the absolute value of a function's definite integral is it's the actual physical area of that space, not the net area. Right. Property 4 says, well, if you took 15 times the integral from, or the definite integral from 3 to 6, right? If that 15 was on the inside times f of x, you could move it to the outside. And you'd have 15 times negative 18, which would yield negative 270 in that result. Right? Again, that's property 4 in action. Do I have any others here? I think I have one more. Now I go back to property 3, sum and difference rule. It says if I want to find the antiderivative, or careful there, the definite integral, I'm going to say antiderivative every now and again because they're all related, we're going to find here in the very next section. But if I want to find the definite integral from 0 to 3, for the difference between f and g, that definite integral operator will distribute itself across that difference to the function f of x and to the function g of x across that difference. Now above we were told this integral was equivalent to 10, and this integral was equivalent to 4. So the integral across that difference is going to be 10 minus 4, or equal to 6 in value. All right. This is just getting us a little used to working with the definite integral notation here, folks. And it's going through those properties of the notation, right? The properties of the calculation, the properties that we should have when trying to understand net area. Right? There's several useful properties in here. I didn't illustrate them all, but I illustrated, I think, the ones that we see most frequently. Right? I don't necessarily see either of these two. Right? Necessarily illustrated. But the rest of these, I think I did. Right? But yeah, folks, that's the definite integral. And as I had noted, where this is going to come in extremely handy, well, first of all, for the rest of the semester, but when we come back to Calc 2, we're going to be looking at application of integration and application of definite integral calculations. This calculation done in quite a few different situations, where in each of those situations we are going to be considering a calculation that is either going to be related to area or net area in some context, in some thought, in some even minute way, but is all going to form initially with something that resembles the right-hand side of how we define the definite integral. All right? We're going to see this right-hand side form for several other scenarios besides just the area trapped between a curve and the x-axis. And in those other scenarios, we're going to be able to also translate those cases into definite integral calculations relative to those situations. And I'll be coming back to rely on this formula to do that. All right, folks. Again, where we're heading and what's next for us here? Well, we're going to look at how to do these calculations using that antiderivative operation, right? Using that antiderivative function. It's going to help us to calculate these net areas. What we're going to find is that antiderivative function corresponds to an area function, right? A function describing net area trapped between the x-axis and the curve that we're calculating the antiderivative for, right? And we're going to see in the next section, again, a really important idea that's kind of given in its name, what's going to be called the fundamental theorem of calculus. And it's going to have part 1 and part 2, fundamental theorem of calculus part 1 and fundamental theorem of calculus part 2. The fundamental theorem of calculus part 1 is going to make the connection between the definite integral and the antiderivative function to calculate this net area. And the fundamental theorem of calculus part 2 is going to give us the methodology, the process for calculating that net area, that definite integral, with that antiderivative function. Part 1 makes the connection. Part 2 gives us the calculation. We're going to see that next time, folks. But with that said, I'm right under an hour, and I am tired. It's actually almost, well, I'm not going to even tell you the time. It's pretty late. But I couldn't sleep. So I said one more video here, and that's what I'm doing. So I will see you hopefully in class, and yeah, I'll be certainly back in that next video looking at the fundamental theorem of calculus. Really, I think the idea that we've probably been building to the entire semester. All right. And we'll talk about that then. See you next time.